Hi, everyone. I'm here today to talk about how we're rebuilding our infrastructure on top of ECS, Docker, and a whole host of other good tools. You have a lot of startups that start with maybe a few founders who have questionable ops skills. Maybe there's an idea, and they kind of hack together something that works. But there's kind of a weird transition period between the point where that startup really starts taking off and there's a lot of growth, and you suddenly have this like fully baked ops team where now you have alerts for everything and auto scaling and auto provisioning, and everything looks a lot more mature. No more commits with YOLO in the title, that sort of thing, you know? So I wanted to talk about how we went through this transition over the past year and kind of what changes we made. Because a lot of folks like Google or Facebook or Twitter talk about how they achieve this at massive scale. But as a startup, you probably don't have those resources or the time to build those sorts of systems. So you can actually achieve a lot of them with a very small team built on top of AWS. To kind of frame the problem here, a bit about me. I'm one of the co-founders and CTO of Segment. And what we do is we're a single source of data for all of your customer data. So the idea is that you send us data, things like clicks, people performing actions on your app or your site, maybe ad impressions, basically anything that you care about that you want to track related to your customers, and then we collect it as sort of a central store and fan it out to any of these different places that you want to use it. Maybe it's emailing them in a tool like MailChimp or Customer.io. Maybe it's analyzing their data in Mixpanel. Maybe it's putting it in a data warehouse. We're sort of the central place for all of that data. To give you a kind of rough sense of the scale that we're dealing with, we process around tens of billions of calls every month coming through our API and then fanning out to all of these different 150 services that we support. We're managing a few hundred instances on AWS and leveraging a lot of different services pretty heavily. But of course, it wasn't always this way. This is a photo from actually our first office, and using office here is a little bit liberal since this is our first apartment. But we had a bunch of whiteboards and a bunch of screens and not a lot of ops knowledge at the time. Basically, my co-founder Ilya, who's the shirtless one there, I'm not in this picture since I'm taking the picture, the two of us were sort of responsible for provisioning our whole AWS setup. So we met with a solutions architect at the time and went about as many best practices as we could, like setting things up in a VPC. And then we were still pretty rudimentary, so we went back to trying to find product market fit. And that actually got us through for a relatively long time. We sort of provisioned all our instances through the AWS UI. We do things as kind of custom one-off things. But over time, as with most startups, we started really approaching a scale where this wasn't cutting it anymore. There were only a few of us who knew how to deal with the backend systems, me, TJ, and Garrett. And more of the dev team wanted to be able to boot their own services, but couldn't really do so in a way that we deemed safe. So about 6 months ago, we decided to kind of restructure the whole thing and think what would happen if we built this system today from the ground up. And so this is that story. In particular, I'd like to talk about 5 major points of this transition and some of the decisions we made when moving to this new production setup. The first one is using separate AWS accounts. Second is how we adopted Docker and containers, which I'm sure you've heard a lot about today. The third is how we actually moved to ECS for running all these containers in different services. The fourth is using Terraform to actually provision everything and make sure the configuration management looked good. And then the last one is using Datadog to monitor and alert for all of these systems running in production. I'll start out with the separate AWS accounts, which was something that my teammate Garrett came up with, and I know several other shops end up doing the same thing. But honestly, it's been one of the best moves we made all year. Before, we'd separate different accounts like dev, staging, and prod by region or by instance tags, but honestly, that's pretty error prone. And there's a pretty high degree chance that one of your devs will accidentally do something on the wrong environment. So instead, we said, put that to bed and said, hey, we're going to use actually physically separate accounts. They won't know anything about each other. So we got actually really good isolation between them. So things running in production have no concept and can't even talk to things running in stage. Additionally, we ended up having a single sort of bastion points, which I'll talk about in a second, where we could basically create user accounts in just the ops accounts and then have a single place where we're provisioning users and then a single place for auditing what those users are doing. And then as an added bonus, we also got consolidated billing and reservations for each of these accounts. So if you want to look in some place like Trusted Advisor, you can figure out what's using what. To generally walk through how this works with my sort of not design approved drawing here, basically everything goes through this ops account, which is sort of our jump or bastion account, if you will. This is where we create all of our IAM users. This is where people log in if they want to do stuff with production. This is if you're a new infrastructure engineer joining the team, this is where you start. And then from there, we use the assumes role API to actually assume roles in different accounts. For those of you who are unfamiliar with IAM roles, they're kind of like IAM users, but they're basically a decoupling from what you're able to do, the policy, versus the user itself. So we can have single IAM users created in this ops account, and then we can create roles in each of the other accounts that they'll auth into. And at the time, we've just separated them into 3 separate accounts. Dev is really our playground, where you can do pretty much anything you want there. No one's really relying on it for anything. So if you want to try out a new experiment, you want to try out using Dynamo, you want to try out using this new service, feel free to go nuts, and you can actually play with it on top of AWS technology. Stage we keep a little bit more locked down because we want this to actually be a good staging environment, so we don't want people to be trying their experiments all the time, and then one person is trying to actually preview whether the app looks good while another person has just broken everything. So for that, we try and make sure everything passes through CI. There's a little bit more lockdown that occurs, and then finally prod is our production account. And it's worth noting that none of these accounts can talk to each other. They're all completely isolated, completely different. The one thing they share is billing and IAM access. And for how that actually works, we can create these different IAM roles in each account where we basically grant access to users in another account. So you can see here, this is a just sample IAM role that we have. Maybe you have like a read-only one for accessing day-to-day, and then you have an admin one for actually making changes. But you can grant access, in our case, to the 3 users in the ops account. So this would be me, Garrett, and Amir. We're allowed to assume the role, which takes on this role and whatever permissions it has. And then the other key thing here is that you can ensure MFA access as well. So you can say, hey, I'm not allowing anyone to assume this role without MFA, which is incredibly nice because if I'm giving someone keys to this admin account or allowing them to make whatever provisioning they want, I can be sure that that's not being used by an attacker somewhere down the line, even if we publish those keys accidentally. How this works in practice through the interface is that you then get this little menu up top saying, hey, I'm right now on the ops admin role of the segment account. I can switch here between any of my stage, prod, or dev accounts pretty easily. And this works pretty well in practice. It's the kind of thing where you can just switch between different accounts and then use whatever you want. There are a few hiccups with the UI where sometimes if you try and switch to something that doesn't exist in another account, it'll route weirdly based upon the hash. But for the most part, it's greatly simplified switching out so you don't have to log out and then log back in. You might be wondering how this actually works from the command line. And for a while, honestly, it was kind of a pain where we'd end up creating IAM users in separate accounts and like sort of defeat the purpose of what we were doing with these separate accounts. Since then, we've actually adopted this tool built by the folks at 99 Designs called AWS Vault. And what this does is it hooks into your AWS config file. So you can use the same sort of config you've been using, saying, I want to auth for this user, I want to source from this other account, I want to switch between these different roles. And you can do that all from the command line. And what's even more badass is that it will auth with the STS system as well. And then it will also request MFA tokens right in your terminal. So you can see here, basically I've tried to exec on the ops account, I want to list all these S3 commands. And the way this works under the hood is basically for any sub-processes that get spawned, first it'll auth with STS, and then from there it will export those as environment variables for your access key and your access secret. It'll ask you for your MFA token, which is required, remember to do anything, and then it will execute the command. So that allows us to switch between these accounts really seamlessly using the CLI with having to create a bunch of different configs or users in those other accounts. And lastly, I touched upon this briefly, but the very nice thing is that it allows you to do consolidated billing as well. When you get to AWS with any sort of large scale, chances are you're going to want to do invoicing for events so that you don't have your credit card constantly being maxed out, and there's a possibility that your account gets shut down, which obviously a deal breaker for any production service. So this just really nicely allows you to enable invoicing for a single account, which I think you have to do through your account rep, and allow you to like break down costs per account as well. So in our case, it's not such a huge deal yet since we only have 3, but for the case where we're trying to add up to n accounts someday, this will allow us to split by teams as well. And if you're using Trusted Advisor, it lets you see which accounts are well utilized and which ones are just sucking up your cost. The next thing I want to talk about is how we actually run those services using Docker and containers. And I'll start off with development and then gradually make our way how we make it to production. So containers, they definitely dramatically simplify the way that we deploy code. I think the biggest thing that they've done is basically democratize the process between the ops team and the development team. Where before, if the development team wanted to change a version of something that was running in production, they have to bug the ops team and say, hey, can you guys update this? Can I like run this with some sort of new thing? Now they basically established a clean API with containers and say, ops team says, hey, if you give me a container, I will run it for you. As long as it runs, that's your responsibility, but I'm willing to run it on top of our infrastructure. And the dev team says, okay, we'll create containers that run and we can change the runtime however we see fit. So that's massively allowed us to speed up our iteration of shipping, because now if we want to say upgrade a node version, we don't have to figure out time for the ops team to upgrade across all machines and then do kind of a hot reload and make sure everything looks good. It's basically up to the dev team to upgrade that in the particular container and then ship the new version. And ECS, as I'll talk about in a second, helps us guarantee safety there when we're actually upgrading. The other benefit is just we get good code isolation and good code mirroring between different environments. So we can ship the same Docker containers in development, we can ship the same ones in staging, and we can ship the same ones in production, which actually gives us much more repeatable builds. Basically, we have a shared segment VM, which itself is a Docker container. When we push updates to it, it pulls them down automatically, and we'll just make updates to that container. Our use of Docker is probably pretty vanilla, honestly, in terms of what we do for our Docker files. We just have a common base image. Most of them are based off Alpine for making like a really small image. We copy whatever binaries in the case of Go or source code in the case of Node into that container, and then we give it an entry point with some sort of configuration or command flags. In all cases, we do configuration through environment variables or flags that are specified in Terraform. Eventually, I think we'll probably move to something that's a little more file-based or something via like console or etcd. But for now, this works pretty well as being like very auditable, so we can tell where things are coming from, as well as being very explicit. The other piece for working in development, as I said, we can use the same containers in development as we use in staging and production. We make use of Docker Compose pretty heavily in development, where we'll pull down various images that we're building for different services. At Segment, we've heavily embraced the microservice approach, where we have a bunch of individual services doing different things well, and so each of those run in containers. Since they're running containers in production, we might as well pull them down and just run them with different settings locally, which is what this script is doing. So basically, each one of our services ships with a Docker Compose file, which we can use. So you can either run your own services or you can run sort of the same setup that's running everywhere else. That's at a high level kind of how the pipeline works. Basically, we have a repo, which has a given service in it. We git push, which pushes up to GitHub. If it's on master, it'll actually trigger a build, or if it's pull requested, which will run through Circle and run a bunch of tests. And then if the tests pass and it's a tagged release, we'll then push it up to Docker Hub. And then I'll get into shortly how we deploy that to ECS, but sort of the long and the short of it is that we update via task definition using a CLI tool or our Slack, which is basically hooked up to the CLI tool. It'll update with the ECS agent and then grab the new version of the task def, and then it'll pull it down from Docker Hub. So actually running these things with ECS. The kind of nice things that ECS gives us, one of the biggest ones is it handles 0 downtime reloads for us. You don't have to bake it into your code anywhere. Basically, when you're booting a new service, what you can do is say, hey, ECS, I want to boot this new task definition. It'll actually boot the new containers before removing the old ones, and then it'll remove the old ones and let the load balancer drain from connections to that instance. You still have to handle a few things yourself. For instance, if it's a worker or if it's something where you want the container to actually specifically close connections before it exits. But for the most part, you don't really have to think about, oh, okay, what if I reload this process? What is it going to do? Because ECS handles that for you. And moreover, it makes sure a particular instance is running or a version of your code is running, which doesn't sound like a lot, but we've had, I want to say like 2 or 3 in-house deployers at this point, and you'd be surprised at how many times without any sort of consensus algorithm, you end up with different versions of code running at different times, which is not good at all. So ECS ensures that, oh, okay, all these containers come to a consensus, and no matter how many continuous deploys are going on, maybe 2 different people are deploying different things, you're going to end up with the same version of code kind of no matter what. A bigger reason we chose ECS over something like Kubernetes or Nomad or Fleet or any of those other schedulers out there is we really like the ECS or the AWS integration. In particular, you get free health checks with ELB. You get CloudWatch metrics for free. You get nice tooling from the AWS API, which we use pretty heavily everywhere else. There's a lot of reasons for it that it just made it a very obvious choice for a shop that is really heavily using AWS and the APIs. And there are a few minor gotchas around ports and scheduling. For instance, if you're trying to run everything on the same port, it exposes it all on the instance. So if you try and boot kind of new containers there, if you don't have extra capacity, your scheduler is going to complain basically indefinitely that it can't add new containers. But for the most part, that's going to be resolved. ECS claims that they're coming within the next like 3 or 4 months. So we feel pretty good about them actually patching that problem. I wanted to give a brief rundown of how we actually use ECS, since different shops use ECS differently. And so at a high level, we actually use Route 53 to give each ELB a service name. So for instance, if you're trying to connect to the auth ELB, that's at auth.segment.local, app.segment.local, nginx, nginx.segment.local. You get the idea. And those are all internal names, so they're not accessible anywhere outside the internet. They're internal ELBs too, for the most part. So it's how all of our services talk to each other. And then each ELB gets registered with a particular service. So in our case, ECS is scheduling these different services across a given cluster. It's running individual task definitions. So let's say it's running the app on servers 1 and 2 there, nginx on 3, and then the auth service on service 1. If we need to update the task definition, it'll then run auth on one of servers 2 and 3, give us 0 downtime reloads, and make sure that we're automatically connecting to each ELB. Why is this good? Well, in particular, we don't need any form of service discovery, right? We can basically just use DNS, which has been working pretty well for the rest of the internet, and then connect to all these different services basically by their host name. That goes through the ELB. There are a few cases where this has a slight gotcha. For instance, say you want to connect to Mongo or something that creates kind of multiple instances for replication. Just having a single big service isn't going to cut it, right? You can't just say the same host name 3 times in a row. So for that, we're still kind of using a work in progress. Right now, we use individual host names for those instances as well, which I'll get to in the Terraform section. But for the most part, it's worked out really well. It means that we don't have to worry about uptime and downtime because ECS handles the ELB cycling for us. And we get free metrics for every service, which is huge. It just means that for any given service, you don't have to worry about things like requests, 200s, 500s, et cetera. Those automatically get generated by CloudWatch. So the visibility is incredible. And speaking of visibility, a lot of folks have asked, how do you separate different ECS clusters? We've heard a bunch of different ways to do this. Some people use like one giant cluster where they want to schedule everything. Some people have individual clusters per service, which is what we do. Basically, for most things, we keep individual clusters so we can actually get good insight into what the load is. And we can more closely sort of form which instances they're using. So for our API, maybe we want to give those beefy instances. Maybe we want to give them large disks so that they're able to actually buffer data in case something goes down. For those integration workers, which are, you can see here, kind of like pegged in terms of CPU, maybe we want to give those like a quicker CPU or more compute optimized machine. So it really helps us give a quick, like, high-level overview of which instances and which services are acting up. And then we have a few sort of general default ones for stuff which is maybe not high load or we don't need as much visibility into that we kind of throw things for the rest of the dev team. Talk about AWS accounts, how we run containers, how those actually get into production versus service, and then kind of the last piece here of actually running different services and provisioning our infrastructure is Terraform. And for those of you unfamiliar with Terraform, Terraform is kind of like CloudFormation on steroids. It basically gives you a really simple way to apply and then change infrastructure in production. And I'd say one of the biggest benefits is actually that it calculates the diff for everything, which I'll talk about in a second. But basically, if it doesn't have to reprovision a load balancer or a particular instance because you're changing some sort of setting, it won't. It'll just update it. So that means that you actually get really, really quick iteration cycles for most things that don't need to be changed. But where it does need to be changed, it'll do the right thing. And then finally, it also has multi-provider support, which I'll talk about once we get to the Datadog section as well. Honestly, we haven't used this too heavily, but if you wanted to plug into DigitalOcean, Linode, any of these other tools, there are a lot of modules built on top of Terraform which make changing that underlying infrastructure easy. At a high level, for those of you who haven't used Terraform, the way it works is basically a dev decides to make their changes to this configuration file, saying how they want to change the infrastructure. Then they run a Terraform plan, which does two things. First, it refreshes from the state, whether it's either local or remote. And the state file is just sort of a big output. You can think of it almost like a CloudFormation file, describing the current state of the world. And then it will calculate the diff. And like I said before, if there's things like tags or instance name, anything which can change without needing to reboot the instance, it'll just do that. And then say, hey, I don't need to change this instance around at all. I'm just going to use my APIs in order to change it there. If it does need to reprovision the instance, it'll actually tell you, hey, I'm going to destroy this piece of infrastructure, say for a security group or new availability zone or subnet ID, and then boot a new one. And then finally, if you're the dev, you plan the changes, everything looks good, you're going to say, hey, I'm going to apply everything and actually push it to production. What this actually looks like, this might be, for those of you unfamiliar with it, a little hard to read. It's actually this HashiCorp configuration language written by the HashiCorp guys, which is sort of similar to a mix of JSON and YAML. It's nice because it provides comments, but is a little more explicit than YAML. And basically what this is doing here is I'm just provisioning a AWS instance, which I've turned my Bastion instance, and then given it an AMI, an instance type, and then a few variables for things like the subnet ID and security groups. And the nice thing is that Terraform with the AWS APIs provide pretty sane defaults. So you can actually provision these instances with pretty minimal amount of config. Here is actually more than is like the bare minimum necessary. And it's nice because it actually makes it so your user doesn't have to care about most of the things that are more advanced unless they really want to. Just in terms of how this looks in practice, we execute our plan. It refreshes against the state, which is either local or remote. And then it'll say, hey, in this case, there's no changes, but if you make some changes, it'll provide a little diff, similar to what git diff would do, saying, this is the changes I'm about to make. Are you sure you're okay with making them? And then you'd apply. Kind of the biggest learnings we had with Terraform, since honestly, it's pretty tricky to get started with, and it is insanely flexible. So there's a lot of places where you can shoot yourself in the foot. The biggest learnings that we've had are creating different modules for each service with good defaults. And modules are just a piece of Terraform which could combine multiple different what they call resources. And so you could create a module, say, for your entire infrastructure. If you want to boot new instances of that infrastructure, you could create ones for services, for ELBs, that sort of thing. The second big one is referencing remote state where we can. Initially, we kept all of our state in this Git repo. That would then, people would make their change, and then they'd push up the repo to other people. Other people would pull it down, plan, make changes, push it back up. As you can guess, with a dev team, we're a small dev team of like 13 people, but once you get to a dev team of more than, say, 3, people start making changes at the same time and actually conflicting. So you definitely don't want to have conflicts in your state for your production infrastructure. So what we ended up doing is started referencing this remote state, which is basically kept on S3, and it's basically atomic, where if you make a change, you plan against that version of that state, and then if you decide to apply, if someone else has made a change in between that point, it'll actually reject the change. And the other two goals with Terraform, we wanted to make it as little work as possible to create a service. I always say that microservices only work if it's actually easy to create them. Otherwise, you're way too tempted to shoehorn whatever new functionality is into an existing service, and it just won't work. And then also make it safe to update, which ECS actually helps a lot with. Going back to this diagram here, off-referenced, for what our services look like, how do those actually look in Terraform? Because it's all good to say, oh, we use Terraform for all of these things, but where the rubber meets the road is a lot more tricky. So this is what a service looks like for any developer who's trying to create a new one. And in this case, I just pulled this Analytics Academy service off of our infrastructure. Basically, Analytics Academy is just a static site. So this one is fairly simple. But first, you'll notice here it has this source for the module. And this is where it's pulling most of the configuration. This is where the sort of module source code lives. And the great thing about these is that they can either be folders or they can be Git repos, just referenced via GitHub. So there are a bunch that HashiCorp has put out there around best ways of booting things like console. Eventually, we hope to open source these, so we could then just put github.com/segmentio, stack, module, service, and reference them from anywhere. But ultimately, they're super modular, so that's something that we really like about Terraform modules. Then we have to give the service a name, which gets propagated to a bunch of other places that we use based upon convention. We give it the image that we're actually pulling from Docker Hub, and so this is namespace with the segment namespace. Eventually, I think we'll move to the ECS container service or Amazon Container Registry, just because it has a little bit better security guarantees than Docker Hub. But for now, we're using this. And then whatever version we want to run. And I mentioned before sort of this idea of remote state. You can actually have multiple types of remote state that you're referencing. And so here we've got this remote state, which we're using as kind of a read-only state. So we're keeping this idea of core infrastructure different from the services that we're actually using. So we might have this site cluster, which other devs can use and run stuff on top of, but they can't touch it. They can't actually upgrade the number of instances without talking to someone on the ops team. And then things like memory and CPU, which we give same defaults for, but allow you to overwrite if you want to. Say if you're running something small in stage, but then something big elsewhere. And finally, the environment, whether it's dev, stage, or production. If you're diving down into this, basically we create this task definition, which again propagates these variables from the upper layer, along with other variables that we provide same defaults for. We create the ELB and the Route 53 name associated with each of these, which we also wrap in our own modules, basically setting a lot of these common things from the remote state, but then passing along where we need to, where things are configurable. Finally, we pull it all together with the service. And so you can see here, this is the ECS service, and it combines this task that we've created with inside the module, as well as the ELB. So those things together, working in concert, actually create our Terraform service here. And so the biggest learnings, definitely use remote state. HashiCorp offers their own version of this called Atlas, where it's actually pretty cool. It'll allow you to plan changes, and then basically someone has to sign off on them and check off, and then they finally get merged and applied. So that's sort of a safety bucket against screwing up your infrastructure. We're using S3 for the moment, which provides similar sort of guarantees, but not quite as good or visual. Definitely use modules for different environments. Before, we had basically two big folders, one for production and one for stage, with all of our custom configuration. And of course, it meant that stage quickly became out of sync with production, so we weren't actually testing things in stage. So if you use modules, then you should be able to reuse them between those two environments, and hopefully just eventually boot up an entirely new environment. You want to use defaults liberally, for sure. Don't require variables where you don't need them, because then the user is going to have to learn this entire API. And as you could see from those previous slides, the HashiCorp configuration language is not the most eye-friendly thing. So you're going to want to try and save on as much of those as possible, and then create a read-only state for remote infrastructure. And kind of the last major learning that we had was actually you want to output a plan that's a binary file. When you're running plan, you can decide whether you want to make changes directly to the state file that you have, or whether you want to output a binary that then you run. And the binary actually ends up being much better, because it actually checks against which version you're running now and which version the remote state has, so that you can ensure that no one else made changes between then and now. Believe me, I'm not paid by Datadog to advertise. But it's honestly the best monitoring tool we found, and one of the best things we'd adopted all year. So if you're not using it now, would highly, highly, highly recommend that you give it a shot. And there are a couple really good things about it. One of them is that the API allows you to script dashboards and alerts, which is something that I didn't really realize the full value of until we actually started dealing with these at scale. They give you free metrics and reporting, along with our toolkit that we've added. So using that, you kind of get a lot of stuff out of the box for free, which is very convenient for the rest of the dev team. And they have excellent integrations for AWS, along with Redis, Mongo, basically console, anything that you care to run. They'll give you dashboards out of the box that are able to customize as well. And so all of our base AMI is provisioned with this Datadog agent, which is built into Docker. So it's able to run as a container. It's able to grab stats from all the rest of your containers. And it's able to pull instances from the machine. or metrics from the machine. As far as the API is concerned, this was something that I hadn't really seen the full value of until we had these metrics. It's a little hard to see here, but since we're sending data to these 150 different integrations, we have a different queue for each one. And unfortunately, NSQ doesn't allow you to tag these queues. Instead, they say, hey, we're just going to send along like a given name for each metric. So we had the option of either forking NSQ, which didn't sound too appealing, or having our own sort of stats-D rewriter so that this could show up well in Datadog. Instead, we said, hey, we'll just script creating these 150 different dashboards in Datadog. Took like a day with a Python script, and then we were ready to go. So this is kind of what it looks like, and we can always just recreate this dashboard whenever we want from our custom metadata. And I'll actually get to sort of the holy grail of this whole infrastructure alerting idea in a sec, but that also relies on the API. The other great thing is that we actually get free metrics for a lot of different services. Metrics are free in kind of two senses. One is that any stats-D stats you're recording, they're transmitted over UDP, super cheap, aggregated on the instance. Basically, we tell our devs, like, use metrics everywhere. Like, if there's ever a case where it's actually slowing down your program execution, then you can sample, which is also built into stats-D. So for the most part, they're just totally free and totally super cheap. So use them because they actually give us visibility into what's going on. The second here is that Datadog also, like I said, plugs into a bunch of AWS CloudWatch metrics. So you can see for a given ELB, how many, the request latency, 500s, 200s, 400s, whether there's any spillover or backend connection errors that are happening and allow you to alert on those. And like I said, we have custom kits for each of our services that chart things like the number of Go routines if you're running in Go using pprof. If you're using Node, it'll actually check whether the event loop is blocked. It'll check stack size, heap, that sort of thing. If you're running a lot of infrastructure, they actually have this sort of host level map or view where you can basically filter by anything that's instance tagged whatsoever. So a lot of time we'll look at a given group of clusters and figure out where the instances are pegged. You can split by availability zone, and here these are colored by CPU. So you can drill into, say if there's an instance, one instance that's just like spiking in CPU, you can really drill in and figure out which one that is visually really easily. In a way that most other tools I've seen don't allow you to do. And this thing is super responsive for our several hundred instances. It'll be interesting to see what happens when we get to thousands of instances, that sort of thing. Finally, what I was referring to as the Holy Grail. Remember before we provisioned all of our infrastructure using Terraform, but we have these alerts that kind of live over in this separate area that aren't connected to anything. What we'd like to be able to do is actually script so that our alerts and our metrics are monitoring our actual production infrastructure, and they're referencing one another. And how can we do that? Well, typically it'd be really hard to do, except for the fact that Terraform recently added a Datadog provider, so that you can actually specify and say, hey, I want to create this dashboard based upon service X, and reference that service directly just based upon what you've provisioned your production infrastructure to be. So this is an early version here of the code that my teammate Vince coded up, and he pull requested the Terraform repo, and then after some changes, I think Monday, they actually merged it in, which is really cool. So soon we'll basically be able to add this to our service module and say, hey, whenever we create a new service, also create a dashboard for that service with the ELB metrics and the ELB latency, and also create alerts for them. So that basically out of the box, if you're a developer, you don't have to think about any of those things at all because they often get missed. So this is something that you can only take advantage of via the Datadog API, and it's something that Terraform makes it really easy to manage the existing state of your metrics or alerts. So we'll be using this pretty heavily going on to make it really easy to create dashboards kind of off the fly without doing any work. Finally, when all the time came to move, we were ready to move from this janky old prod account to this new thing, which had all of our instances, all of our configuration. It was all set up. And that process actually went very smoothly because we sort of got over a few gotchas in the first place. The first thing we did was actually peer connections between our two VPCs to make sure that they could talk to each other. So we booted up all the services in our new production account, but they're still talking to databases in the old one, and some that were replicating in the new one to the old one, just so we could switch kind of seamlessly. One thing you want to make sure if you're ever changing out this sort of infrastructure is to actually pre-warm ELBs, which is something that I hadn't known about until about 2 years ago. Accidentally deleted a production ELB that was serving a lot of traffic, and our entire API went down for about 40 minutes while instances like booted up. Fortunately, that hasn't happened like ever since then because of all these safety checks that we put in place. But it's the kind of thing to be really cognizant of. If you're dealing with something where you're dealing with thousands of requests a second, you're going to have to ask for that ELB to be warmed, or you're going to have to warm it yourself with test traffic. Which we did actually a combination of those two things. We asked AWS to pre-warm it, which was great. They took care of that. But then we also gradually ramped traffic and make sure that nothing was going wrong with our API. Just so we could see and verify for ourselves that all of the traffic was being ramped properly. This is pretty much everything that we've done up in the past like 9 months until now. And kind of what we have planned further is actually planning and applying via CI. So if I'm a developer, we don't need kind of keys everywhere. There's something where we'll plan, submit a pull request. If the pull request looks good, it'll actually output that plan to S3. And then we have some sort of admin who's looking over the plans and figuring out, oh, okay, does everything look good? And then they just apply them and say they're good. Secondly, we want to further decouple our services from our core infrastructure. Something like Convox or similar, where we're able to say, hey, I want to basically change around the service configuration without having to touch all this kind of core infrastructure. We might continue using Terraform for that, where we say anyone can access the service repo, but if you want to touch core infrastructure, that's something that's remote read-only state. Like I said, we want to add Datadog monitoring to those service definitions so that if people want to boot new services, they don't have to think about that because it often gets forgotten. And we want to mirror our Route 53 entries. That's kind of the one last piece that we haven't actually moved over yet. And then the ability to create just N accounts. Right now we have 3, but it'd be really great if we could just spin up new environments all the time and script that totally, and then not have to worry about any individual account.